Hey guys, today we're going to look at slope fields, which is basically a field of these little line segments representing the slope of the function. Now, why would we need that? Why can't we just find what the function is and graph it? Well, this is an example where we can't actually go back and find what that original function is. This is a differential. We looked at differentials before. We looked at the ones that are separable. And then we looked at some applications of those differentials. So if you recall, we solved problems involving Newton's law of cooling. The rate at which the temperature changes, or the derivative of the temperature equation, is proportional to the difference between the temperature of the object and the temperature of the surrounding environment. Or an exponential growth problem says the rate of change of the population, the derivative, is proportional to what the population is at that moment, k times p. And then we were able to actually separate that out and have our dy on one side, our dx on the other side, and then integrate both sides and eventually come up with the equation y equals such and such. This is not one of those cases because I can't separate this out. Yes, this is dy over dx. I can move my dx over here, but I can't move my y over there by dividing or multiplying. I'd have to subtract, and there's nothing that I can do with a dy minus y. I don't know how to integrate that. The only thing I can integrate is something times dy. So we're kind of stuck. A slope field allows us to get an idea of what the function looks like without actually being able to find the function. So you see on your printed out notes that there's a table over there. I'm not going to write down all those numbers. You feel free to fill those in. But I am pretty much finding the slope, what y prime equals, at all of these different locations. So the first location that's listed there is at the point -2, -1. This tells me how to find the slope at any point. I'm finding the slope at all of these points. I'm going to draw little line segments representing that. So at -2, -1, if I plug that in, 2 times -2 is -4, plus -1 is -5. So at this point right here, y prime is -5. My slope is -5. Okay, so I'm just drawing a little representative segment there that has a slope of -5. Okay, just a really steep slope. It's hard to get that. You know, you have a better graph that you can kind of go down 5 and right 1, but only draw that little segment right around the point -2, -1. Just a little segment. Okay, if I go to -2, 0 right here, well, this tells me to do 2 times -2, which is -4, plus 0 is -4. So the slope here is -4. Just draw a little line segment. At the point -2, 1, 2 times -2 is -4, plus 1 is -3. The slope here is -3. So down 1, 2, 3 over 1. So I'm thinking it's that angle right there. Just draw a little line segment. Okay. -2, 2. -2 times or 2 times -2 is -4. Plus 2 is -2. So at this point right here, the slope is down 2 and right 1. So I'm imagining connecting those dots, but I'm just drawing a little line segment. Okay. And I'm going to follow through and keep filling in all of these points and drawing little line segments. So my next spot is -1, -1. So I put that in there. 2 times -1 is -2. Minus 1 is -3. So at that point right there, my slope is up 1, 2, 3, and left 1. So it's connected to that point. Just trying to picture what that looks like. There's my slope of -3. -1, 0. 2 times -1 is -2. Plus 0 is -2. Down 2, right 1. So it looks like that. Okay, I know these look very similar, but the angles are getting less steep. All right, -1, 1. I get -2 plus 1, which is -1. So this point right here, I get a slope of -1, down 1, right 1. Okay. -1, 2 gives me a slope of 0. Okay, because I have a slope of 0 there. All right, I'm going to speed it up a little bit. I'm just plugging these numbers in, doing 2 times the x value plus the y value. So I am at 0, -1. I get -1. Okay? 0, 0, I get 0. 0, 1, I get 1. 0, 2, I get 2. Okay? 1, -1, I get 1. 1, 0, I get 2. 1, 1, I get 3. And 1, 2, I get 4. 2, -1, I get 3. And then 4, and then 5, and then 6. It's getting steeper. All right, so this actually represents what the function would look like. Okay, so if I'm given more information like, hey, the original function goes through the point 1, 1. Well, then I can kind of guess at what that's going to look like. It's going to have this slope, okay? So it's going to look like that. But as I go down here, my slope actually gets less. And eventually it's going to become 0. And if I go past this way, it goes like this. So I'm thinking, and actually it looks like it might go like this. Okay, purely guessing, I'm guessing that my function would look something like that. If I knew it went through that point, I'm just going to follow what the slopes say. As I go this way, my slopes are actually getting closer to 0, and then I go this way. And we're going to get more practice at doing that, okay? But that's the purpose. I can kind of visualize what it's going to look like if I know at least one point it goes through. Now, a lot of the ones we're going to do are also going to be separable differential equations, so we can actually figure out what that original function is. So we're going to create slope fields, we're going to use those, find tangent lines, and do several things on them. And hopefully that'll get you ready for any question that you're asked on the AP exam. So, number 2, it tells us how to find the derivative at any spot. It says the derivative is the x divided by the y. And this problem is a separable differential equation, so that means we can do letter B and letter C later on for this problem. So my derivative is x divided by y. We're going to graph some of these points. It looks like we're going to -2, -1, to 2, 2. So we're doing all these points right here. We want to find the slopes at all those values. And you guys have the table there. I normally don't write the table. I just go ahead and start drawing my little line segments. So at -2, -1, I'm taking the -2 divided by -1. I get a +2 for my slope. So I'm kind of imagining going up 2 and right 1, and my line would connect that way, but I'm just drawing a little line segment at the location that has that derivative. All right, and then at -2, 0. So -2 divided by 0 is undefined, but we know that when we have a derivative that's undefined, that's a vertical tangent line, so I have a little vertical tangent line there. -2 divided by +1 is -2. So I'm down 2, right 1, kind of imagining that. -2, +2 is going to be -1. Okay, I'm going to continue on. Now I'm going to go to -1. -1, which is +1 for a slope. -1 divided by 0 is undefined. -1 divided by +1 is -1. -1 divided by 2 is -1/2, so it's down 1, right 2. I'm imagining connecting those. Okay. 0 divided by -1 is 0. 0 divided by 0, okay, careful there. That's indeterminate, okay? So that's not a vertical line or a horizontal line. It just does not exist there, okay? So I'm not drawing anything at that spot. 0 divided by 1 is 0. 0 divided by 2 is 0. I'm on to my next spot. 1 divided by -1 is -1. 1 divided by 0 is 0. And you might want to fill the other ones in. Okay, 2 divided by 0 is 0. So I usually fill in the easy ones. 1 divided by 1 is 1. 1 divided by 2 is 1/2. So down 1, left 2 would be that. Just trying to picture what that would look like. 2 divided by -1 is -2. Connects up to that spot. 2 divided by 1 is 2. 2 divided by 2 is 1. Okay, so this is my slope field. So I sketched my slope field. Letter B says find the solution to the differential equation with the initial condition f of -1 equals 2. So it's telling us that when x is -1, the y value is 2. We know our function goes through that point. So I can kind of see what's going to happen. Looks like it's going to curve like that a little bit. Okay? But we can actually solve this differential. So let's review doing that. I'm going to write this is letter B now, as dy over dx. That's what y prime equals. It's another way of writing it. It's more beneficial to write it this way when we solve a differential. Equals x over y. I want to separate my variables. I want to move y to the left. I can do that by multiplying by y. I want the dx to the right, so I'm going to multiply by dx. I'm going to leave the x over there. And once I get them separated, I'm going to integrate both sides. The antiderivative of y is 1/2 y squared plus c, but I don't do plus c on both sides. I only put plus c on one side, because when I subtract that constant over, I get a constant. The antiderivative of x is 1/2 x squared plus c. So if I solve for y, I'd multiply everything by 2. Gives me x squared plus 2 times a constant is still a constant. And then I take the square root of both sides, and I get y equals plus or minus the square root of x squared plus c. So technically, in this problem, I know that because it gives me the point -1, 2, the y value is a positive 2, I know I'm going to use y equals a positive square root of x squared plus c. So I know it's this because the y that I'm given is positive. Okay, right? I'm told we have the point -1, 2. Okay, well I actually can find c, because I can plug my -1 in for the x, and I know that the y is going to be a 2. So we square both sides. I get 4 equals 1 plus c, so c is 3. And so my differential equation for this problem is y equals the square root of x squared plus 3. Okay, so that's the answer to letter B. Letter C, something else that I'm going to have to do is write the equation of tangent lines. Well, I have all of these slopes figured out. So if I know a point that my line goes through, like the point -1, 2, I already know the slope here is -1/2. So my tangent line, this is letter C, my tangent line is going to be y minus 2 equals my slope at that point, which since I already had my table filled in, my slope at that point is -1/2 times x minus -1. There's my tangent line. So some other things you're going to be asked to do. You might be asked to, can you approximate, so this is like a letter D, approximate the value of the function at x equals -0.5. Okay? So we can use the tangent line to approximate that. So it's, the tangent line, if we follow that, right, this is my tangent line. If I graphed it on here, it's that line right there. And I can use tangent lines to make approximations if I don't know what the actual function is. So let's pretend we didn't figure out what the function was. The tangent line, I can find the y value by plugging in my x value. Let's just follow that and get an idea of what the value of our function is going to be. So I have y minus 2 equals negative 1/2 times 1/2, because 1 and negative 1/2 is 1/2. So that's negative 1/4. We add the 2 and we get y equals 1 3/4. You can kind of see that on here. At negative 1/2, we're about 1 3/4. So that would be an estimate. Okay? The exact value would be, we just found what our function was. So the exact value, let's just say this is like a letter E, the exact value we can use our function here. We would have y equals the square root of negative 0.5 squared plus 3. Okay, so that's 3.25, right? Because that's 1/4 right there. So 3.25, the square root of 3.25 is 1.803. That's the actual answer. We're pretty close with our estimate, 1.75, 1.803, because the function, if we graphed it, now that we know what it is the square root of x squared plus 3. It would actually look like this. Okay, right there it would have a slope of 0. It's going to go like this now if you follow that out. Okay, that's what that graph would kind of look like. Now I knew that my estimate was going to be an underestimate. I knew it was going to be lower than the actual value, because if you see what's happening with that curve, how as we progress, the slopes are actually increasing in value. That's talking about the concavity of our function. Okay, since that's going to be concave up, if I would draw a line connected to that and use that line to approximate, that line will always be underneath the actual value. Okay, so that's something else that you should be aware of. When you do approximations, you should be able to determine whether it's an overestimate or an underestimate. Because of the way this is curved, I know that if I'm using my tangent line, it's going to be an underestimate. It's going to be underneath my value. If my function was curving like this, and I find a tangent line, okay, if it's concave down and I use a tangent line to approximate, anything on that tangent line would be an overestimate of what the actual value is. So a lot of extra things I put on here just because that's the kind of stuff you should be able to answer. And you'll get some of those on your worksheet, and I'll have the answer key on there. So let's do one more problem together, and then I will set you off on your own. Something else that will definitely come up on the AP exams, they may have a slope field already made for you, and they'll ask you to match the actual equation. You have that on your worksheet. So if that doesn't make sense, please ask when you have a chance to ask me, maybe Friday or whenever you get a chance. All right, this next one is the derivative is 2 times x times y. This is another separable one, so we can answer some of those other questions, like actually solve the differential, find the tangent line. We always can find the tangent line. So the derivative is 2xy. All right. So if I start sketching my slope field, -2, -1. I'm plugging all these in. I'm multiplying them all together. So -2 times -1 is 2, times 2 is 4. The slope here is going to be 4. At -2, 0, I'm going to have 0. And whenever x is 0 or y is 0, I'm going to get 0. So I know that all of these spots, I'm going to get zeros. There's that, I'm going to get 0, 0, 0. Okay? So a few things to pay attention to. If you see a slope field and you see all these horizontal lines, look at where they are. Because where they are, the fact that you're getting 0 as the slope will help you determine what the equation is going to look like. I know it's not x plus y. It's going to be x times y for this one. All right? The more problems you look at, the easier it's going to be to identify the equation and what the field should look like. All right, so let's fill in the other ones. If I have -1, -1, that's 1 when I multiply, times 2 is 2. It's going to look like that. If I do 1, -1, that's going to be -2. 2, -1 is going to be -4. Okay, let's jump back up here. -2, 1 is going to be -4. -1, 1 is going to be -2. 1, 1 is going to be 2. 2, 1 is going to be 4. Okay, back over here. -2, 2 is going to be -8, so really steep. -1, 2 is going to be -4. 1, 2 is going to be +4. 2, 2 is going to be +8. Okay, so we have a little slope field that we created. Okay, most of the time you're going to be asked to write the tangent line first. So letter C says write an equation for the tangent line to the graph of f of x at x equals 1. And we do need to look at the previous question because it says that it's crossing at the point 1, 2. So I'm pretty much knowing that my function crosses at the point 1, 2, and I can create the tangent line there because I know everything I need. I know the point that that tangent line is going to go through, and I know the slope of my tangent line. The slope of my tangent line is going to be a +4 at that spot. Is that right? Yeah, +4. So, letter C, I'm doing letter C first, just because I know that usually they ask for tangent lines first. My tangent line is going to be y minus the y value 2 equals the slope, which I know is 4, times x minus 1. That's my tangent line. If you want to simplify that a little bit, that's 4x minus 4 plus the 2 is -2. That's the equation in slope-intercept form. So if I drew that, right, we'd have, it starts at -2, it goes up 1, 2, 3, 4 over 1. That makes sense. There's my slope of 4. Okay, so that's my tangent line. Just pretend that was straight. Okay. We might use the tangent line to make an approximation. So like we could approximate the value when x is 1.2. Usually we're going to pick something close to the point we know of, close to where we centered our tangent line. And to make that approximation, we just plug 1.2 in here and we figure that out. And then sometimes it's going to say, well, we can solve the differential. So go ahead and solve the differential. dy over dx equals 2xy. To separate that, we're going to divide by y, 1 over y dy. We're going to leave the 2x over there. We can now integrate both sides. We get the natural log of y equals x squared plus c. Use e on both sides, so we get y equals, remember this? If it's e to x squared plus c, it's like e to the x squared times e to the c, e to the x squared times a constant, okay? That's what our equation is. That's the solution to our differential. Now we do know that it goes through the point 1, 2. So I can plug that in, I can find the c value. So the y value is 2 when we plug a 1 in. If I solve for c, I end up with c equals 2e to the negative first, or 2 divided by e. So that's my c value, okay? If I plug that back in now, I have y equals 2e to the negative first, e to the x squared, and when you multiply and you have the same base, you can add exponents, so we have 2e to the x squared minus 1. So that's my differential. I can use that to find the exact value when x is 1.2. So a lot of times we'll approximate the value using our tangent line, find the exact value, make a comparison. By the way, I know that the tangent line would give me an underestimate of the actual value because of the way this is curving. If I follow what my slopes are doing, yes, the slope is steep there, but as I follow that down, my slope then is going to change to a 0. So I know the actual graph, like the graph of 2e to the x squared minus 1, I know it's going to do this. It's going to have a slope like this. The slope gets steeper as I go up there because, look, I'm multiplying. The slope gets steeper as I progress right and up. And then as I come back down, that slope gets shallower, okay? And eventually, it's going to be 0. And then as I progress this way, now it's going to be getting steeper, negative. So I know it's going to do something like that. Okay? All right, that's good enough for today. You guys need to practice some of this stuff. Please come to the virtual meetings if you're having problems so that I can answer any questions, and maybe we can even do some extra examples together. All right? Take care. See you next time.